All right, so what we have here is the first of the examples that we saw in the first lesson, f of x equals x squared minus 4 over x minus 2, with our target value of 2. So I took the liberty of writing in the table of values that we use to evaluate the limit numerically. But what I've done now is I've added the graph to it. The graph of the function can be obtained using the graphing calculator or by algebraic methods. In this case, the obtaining of the graph is not the point. You guys have learned how to do that in previous classes, so I'm not including it on the video here. I can certainly address any questions you have as to how the graph was obtained during a Zoom session or in response on the in comments on the discussion thread. Now, the idea here is to look at the limit from a graphical point of view. So what the table does is it takes an x value the same distance to each side of the target and finds the y value that goes with it. Those 2 points actually correspond to these 2 points. X is 1, y is 3. X is 3, y is 5. Now, because of the scale of the points, because some of them are going to get very, very small, very small decimal values, it's going to become very difficult to draw in all of them. So the next pair of points moving in closer, now we're only 1/10 to each side, 1.9 and 2.1, and the y values from the function that go with them. Those correspond to these 2 points, getting very, very close in there. Now, I can't really go any further detail than that on this scale. I would have to do, as we had seen in the one video in the previous lesson, I'd have to expand the scale and to be able to get into that finer detail. But that's not really what the point is here. The point in doing in finding a limit graphically is that we don't have to look at x and y as separate things. We can actually look at them at the same time by looking at a progression of points. So rather than look at the x values approaching 2 and then separately what do the y values approach, the whole purpose of the graph is to take every x and y value that's associated with each other and look at them at the same time. So this single point right here gives us our x and our y at the same time. And therefore, if we're looking at a progression of x's and a progression of y's, we're looking at a progression of points. The idea is that the first point might be here, the next one is here, and so on and so forth. So what we essentially have going on here is we're walking along the graph of the function from further away, approaching our target x value of 2. From the right side, we're doing very much the same thing. We start some distance away, usually a whole number, but it can be further or closer. Again, the scale is all relative. We're always going, wherever we start, we're always going to get closer. So if we walk along the graph this way, we're tracing this pattern of points. And if you look, these 2 arrows, these 2 tracings of the graph are meeting up at the same point. That's how you know the limit exists. If you can trace the graph from the left side of the target value towards the target value, and you can trace the graph from the right side of the target value towards the target value, the 2 tracings should come together at a single point. Now, whether or not there's an actual point there is another story. As the definition of a limit was established in the previous lesson, the existence of the function at the target value is not required. It may exist there, it may not. The idea of the limit is not to use the target x value itself, but to use the trend of values around it. So as long as we trace from the left side and from the right side, and those 2 arrows come together, then the limit does exist. Now, the graphical approach is lacking in one major way. It is very difficult to identify the y value, the actual value of the limit in many cases. In some cases like this, I've drawn that graph as precisely as I could. And if you have a very precisely drawn graph, you can probably nail it down pretty accurately. And considering that most examples tend to have a nice answer, a nice value, it's usually pretty obvious what it's going to be. That being said, there are many functions out there that do not have nice y values. And what if we weren't doing it on graph paper? What if we didn't have a grid? What if we didn't have this grid line here to trace over and say, hey, look, this point where the two arrowheads would meet seems to have a y value of 4. Okay, we can see that here, but what if there wasn't a grid line to trace over? How do we know that that point isn't actually at 3.9 or at 4.1 or something like that? I mean, yes, we have the table up here, but my point is that there are strengths and weaknesses to each technique. And I'll talk about them more later. For now, what I want to do is really focus on just the idea of verifying what we already know from the table of values, that the limit exists, and if possible, finding its value. So our second example was f of x equals negative 2x squared plus 5x minus 6. And again, I've written out the table of values from the first lesson, and I've drawn the graph below. Now, our target this time is x equals negative 1. So what we need to do is start somewhere to the left of it and trace the graph towards x equals negative 1. We're also going to start somewhere to the right and trace the graph towards negative 1. And once again, what we see is those two arrowheads are coming together at the same point. They're both meeting up point to point, and they're meeting up here. This is a perfect example of why the graphical method is not the best at finding the value of the limit. This clearly shows us it exists. The arrow coming from the left and the arrow coming from the right are meeting up at the same place. This limit exists. But look at the scale. Every 2 blocks on here is 5. So negative 5, negative 10, negative 15, negative 20, negative 25. So what exact value is that? See, now, even on graph paper, that's between the blue grid lines. We might take a guess and say, well, it looks like it could be about negative 12 or negative 13, but how do we really know? So the graph is an unreliable method for finding the value of a limit. However, there is nothing faster when it comes to simply saying, does the limit even exist? So let's look at a couple examples where the limit does not exist. Again, examples from the previous lesson. This one is the other rational function, f of x equals x squared minus 49 over x squared minus 10x plus 21 at the target value of 3. In this case, again, from the table of values, what we saw is that the output values were not approaching a finite value. If anything, they're getting larger and larger and larger. In fact, every time we move a power of 10, every time we reduce the power of 10 that we are using and get closer and closer and closer to 3, basically, every time we stick another 9 on the end of this, we stick another 9 on here, except sticking a 9 in the decimal side, every additional 9 is actually smaller. Sticking an extra 9 on this makes it bigger and bigger. We go from a 9 in the ones place to a 9 in the tens place to a 9 in the hundreds place to a 9 in the thousands place. Eventually, we're going to have a long string of 9s there. So we could say that the values are approaching negative infinity, and therefore the limit does not exist on the left side. Likewise on the right side, where in this case, the pattern is more like we're sticking a 0 in between the 3 and the 1, and we're sticking zeros in between the 2 1s in the output value. So eventually we're going to have a 1, a whole load of zeros, and then a 1 at the end of it. So the values there are approaching a positively infinite number. So the limit there does not exist. And as we had seen in the previous lesson, if the left side limit does not exist and or the right side limit does not exist, then the two-sided limit does not exist. Well, sure enough, if we trace this graph, and here is, we usually would draw this in with a dashed line for an asymptote. If we trace this graph approaching our target value of 3 from the left, and we trace the graph approaching our target value of 3 from the right, these arrowheads are not at all meeting point to point. In fact, they're going in as vastly different directions as you can get, which is not actually relevant how far apart they're going. All that matters is, do they come together? If they do not come together at a single point, then the limit does not exist. One last example here. The fourth example from our last lesson, the piecewise function. F of x is equal to negative x squared plus 4 for all x values smaller than or equal to 1, or f of x equals 2x minus 1 for all x values that are greater than 1. And our target value was 1. Once again, what we see here is tracing from the left towards our target value and tracing from the right towards our target value. In this case, neither of the arrows is going infinite, but they're definitely not meeting up at the same point, which does coincide with what we saw when we did this numerically. Coming from the left side, these values seem to be approaching 3. Coming from the right side, those values seem to be approaching 1. So even though the left side limit exists and the right side limit also exists, they do not equal the same value. Therefore, the two-sided limit does not exist, and sure enough, the arrows do not meet up at the same point. So, what have we got here? So far, we have two methods of finding limits. We have the numerical approach, which literally means to examine numbers, examine actual values of the function, inputs and outputs. We are told the trend of x values in the nature of the limit. The x values are supposed to approach 1. Our job is to see if the output values approach a specific number. Numerically, this can be somewhat time-consuming. We need to evaluate the function, which, yes, with the calculator can be much quicker. With the scientific calculator, it takes a little longer, but it's still reasonable. For some of these functions, like the rational ones in particular, evaluating the function at some of these decimal values would be a little ridiculous. So the numerical approach is solid. It will identify whether the limit exists, and it will find the value of the left side limit, the right side limit, and the two-sided limit. Or it will show you that they don't exist. It is very solid. It's perhaps the easiest to grab onto because it deals with concrete values. But it is slow. The graphical approach is fantastic in that it is very, very quick to see, does the limit even exist at all? But it may be unreliable at finding the values of the limits, whether it's the left side, the right side, or the two-sided limit. As we saw with the parabola, it all depends on how the point matches up compared to the scale on the axes. Which means anytime we'd be looking at the value of the limit being a fraction or a decimal, or in a case like this where the scale does not go by ones, even though the value of the limit is the whole number or the integer negative 13, it's hard to identify that value definitively on the graph. So the graphing approach is quick to identify the existence of a limit, but not necessarily reliable on finding the value of the limit. One of the advantages of the graph, though, as opposed to a table of values, what if I change the target value? If I change the target value for a function, I need to come up with a whole new list of input values and then go through and calculate the output values for those new input values. So I have to basically redo the entire problem from scratch, even for the same function, if I just change the target value. But with the graph, all I have to do is move to a different location. For example, if I change this function to have a target value of 4, This is how quick and easy it is. Trace from the left, trace from the right. If they're meeting up at the same point, the limit exists. There it is. That fast and easy to switch target values and still see that the value of the limit exists, or that the limit does exist. The value, however, well, again, depending on the scale, that might be something we can identify clearly, and it might not be. In this case, I would not call that very clear. It looks like it might be somewhere around -18, but we don't really have any way of knowing for sure without actually doing some calculations. If I were to have to build a table of values for this, I would have to do 4 minus 1, and then 4 minus 0.1, and then 4 minus 0.01, etc. And on the other side, I'd have to do 4 plus 1, 4 plus 0.1, 4 plus 0.01. So I have to find a whole new set of input values and then calculate a whole new set of output values. Will I get it? Yes. Will I get the value? Yes, I will. But it will take longer. So good and bad points to each. Numerical approach, easier to grab onto. Concrete values, it will always find the value of the limit exactly if that limit exists, or it will always show you that the limit does not exist. The graphing approach is faster for identifying the existence of the limit, faster for switching from one target value to another, but it is very unreliable in finding the value of the limit if it exists. So they both have good and bad points. That being said, an upcoming lesson will deal with finding the value of a limit algebraically using mathematical techniques such as evaluating by substituting the value in, or other algebraic techniques such as factoring or simplifying. That one will prove to be the most broadly useful method, and it's the one we will use most often. That being said, the numerical and graphical approaches should never be forgotten. We will come back and revisit them many times because they are easier to grasp the concepts of, or it's easier to grasp the concept from those two approaches. And then once we have a better feel for the concept, an algebraic approach becomes doable. So again, you can watch this video as many times as you need to. You can just go back and look at the individual examples, but this one doesn't have a PowerPoint slideshow because everything was very visual with the graph. So that does happen sometimes. When the lesson does have more visual aspects to it, you will see more videos associated with it. This one tends to be entirely visual. So again, I hope this was helpful. I hope it gave you another perspective. I like using the same examples. I tried to give you a broad array of examples, different characteristics, different things that might happen as you work with these functions.